Human beings are about to enter into a new and unexpected frontier in space: asteroids.
Asteroids hold the answers to many of the secrets that can help us to understand our own planet.
These small rocky worlds could offer new opportunities, such as the ability to mine their resources or to use them as pit stops for future space exploration. However, they also pose a danger to the Earth that could eventually cause a planetary catastrophe, like the one that wiped out the dinosaurs.
There was a 10-kilometer asteroid 60 million years ago that hit Earth. Presumably we could have another asteroid impact like that at some point in time in the future.
We are now starting to prepare for that unlikely event by tracking the closest asteroids that could threaten our survival as a species. But there is still much to be done.
Right now, NASA has several ground-based surveys that use telescopes to scan the sky and look for threatening asteroids. They're trying to find all the asteroids that might present a threat to the Earth in the future.
Asteroids could also help us solve great enigmas about the origin of the solar system and how the planets were formed. We still don't know if they played a key role in delivering elements of life to Earth.
Asteroid Bennu is an interesting asteroid. It's the type of asteroids that could have brought life to Earth in its early days of formation.
Several missions from NASA, ESA, the European Space Agency, and JAXA, the Japan Aerospace Exploration Agency, have recently studied some of these mysterious celestial bodies and have made amazing discoveries.
The Lucy mission is going to be the first mission ever to explore the Jupiter Trojans. And we are going to actually get a close-up view of 6 different Trojans in this one mission.
In the near future, asteroids could become potential resource targets, which might kick off a new gold rush in space.
From our perspective today, that's a limitless source of resources out there in space. And so there's a lot of money to be made out there in space.
In the coming decades, we will witness a total revolution of the space industry. The exploration and future mining of asteroids will undoubtedly open up totally new possibilities. After more than 2 years of travel, on December 3, 2018, the OSIRIS-REx probe finally reached its target, the asteroid Bennu.
Asteroid Bennu is a carbonaceous type asteroid, so that means it's predominantly made of carbon, much like we are here on Earth and what primarily Earth is made up of.
The culmination of this NASA mission's adventure will occur when the spacecraft sampling arm touches the surface of Bennu, collects some asteroidal material, and brings that sample back to Earth. This tiny sample will allow us to answer big questions, like where we come from and what is our destiny. Bennu hides secrets about the history of the Sun and planets, as well as the origin of life, since it, like all asteroids, is the leftover debris from the solar system's formation process.
Asteroid Bennu is an interesting asteroid to study for a number of reasons. It's the first carbonaceous type asteroid that we've gone out to collect the sample from, and carbon type asteroids are the type of asteroids that could have brought life to Earth in its early days of formation.
Bennu is just one of the hundreds of thousands of asteroids that float in the space in our solar system. These tiny rocky worlds are irregularly shaped, though a few are nearly spherical, and they are often pitted or cratered.
So most asteroids are located in a belt between Mars and Jupiter that we call the asteroid belt.
However, there are more asteroids in other locations. The so-called Trojans are asteroids that share an orbit with a larger planet, but do not collide with it.
Trojans are just objects that happen to be at what we call a Lagrange point of a planet. The Lagrange point is 60 degrees before or after. And the way to think about it is that if you take a planet and the sun, the gravitational force of an object at exactly 60 degrees between those two objects, plus the centrifugal force of rotation, all cancel out. So if you put something at that 60-degree point, it'll stay there forever. And so these Trojans, therefore, are leftovers of the formation of the planets. And that's what makes them so interesting, is that they're an ancient population that shared an orbit with Jupiter.
The main population of Trojan asteroids are the Jupiter Trojans, which is thought to have as many asteroids as those in the asteroid belt. There are also Mars and Neptune Trojans. However, they are not as numerous as the Jupiter ones. The other major population of asteroids is the near-Earth asteroids.
There's also near-Earth asteroids, and these are asteroids that cross the orbit of Earth. So they're ones that could potentially hit Earth.
The near-Earth asteroid population is about 1,000 times less populous than the asteroid belt. The main asteroid belt has about 1 million objects larger than about 1 kilometer, and the near-Earth object population has about 1,000 objects larger than 1 kilometer.
However, not all asteroids that float around our solar system belong to one of these populations, near-Earth asteroids or Trojans, or are trapped in the main asteroid belt. There are rare exceptions. On October 18, 2017, an unexpected discovery shocked the international scientific community. Astronomers discovered that a very weird asteroid passed by the Earth.
This asteroid seems to be at least 3 times as long as it is wide. It is possibly as much as maybe 8, 9, or 10 times as long as it is wide. This is something we have yet to see in our solar system, and how it gets produced is something we're not sure how to do this at this point.
The object was initially thought to come from the Oort cloud, a region far outside the solar system, which can have extreme orbits that take them careening through the inner solar system at speeds exceeding 37 miles per second. This strange celestial body was so significant because it moved at the astounding speed of 54 miles a second, too high to have come from our solar system. The conclusion was clear. It had to have originated from another solar system, making it the first ever discovery of an interstellar object. They named it Oumuamua, which means something like first distant messenger in Hawaiian.
Oumuamua is the first interstellar asteroid we've ever seen. So this is an asteroid that came from another solar system. And it came and it passed through our solar system and is on its way out of our solar system. And that's really amazing because we live at a unique time when our telescopes have gotten better and we're scanning the skies regularly and we're able to detect this first interstellar asteroid. It is likely that other objects have passed through our solar system and we just never were aware of it.
Perhaps it is a messenger from another star system, but what can it really tell us about where it came from? Since it was moving so quickly, the time available to study it was extremely short. As a result, soon after its discovery on October 24th, a wild race began between astronomers from all around the globe to obtain telescope data and unveil its secrets. We were able to analyze Oumuamua's chemical composition using photometric colors and spectra that revealed that it has a reddish color and might have come from the inner part of its original star system. However, The great mystery surrounding this interstellar object was its extraordinary speed of 54 miles per second, much higher than any other object from our solar system.
That object had anomalously large non-gravitational forces. So that was a little unusual. With comets, when you see non-gravitational forces, you tend to see dust produced because the gas is escaping and it lifts the dust off the surface. The interesting thing about this object is we didn't see any dust. So the question is, how can you get gas escaping and not produce dust? And that's telling us something that this object is unusual, at least compared to objects that are made in our solar system. And that's sort of a mystery.
Although we don't know Oumuamua's exact composition yet, we know the composition of asteroids that have been observed and studied for decades. Most asteroids fall into the following three categories: C-type, S-type, and M-type. C-type, or carbonaceous asteroids, also known as chondrite asteroids, are the most common. Their composition is believed to be similar to that of the Sun, although they lack hydrogen, helium, and other volatile compounds. They are dark in appearance, and they are among the most ancient objects in the solar system. S-types, or stony asteroids, are made up of silicate materials and nickel iron. They account for approximately 17% of all asteroids, and they are the second most common.
One is one we call S-type. These are often ones that were referred to as more stony type objects. And they we think are very similar to a type of meteorite that's very common that lands on the Earth called ordinary chondrites.
M-type asteroids are metallic and much brighter than C-type asteroids. They are made of nickel, iron, iridium, platinum, gold, or other precious metals, either pure or mixed with different amounts of stone.
M-type asteroids are very unusual. Some of them may actually be metal. They may actually be produced in the interiors of asteroids. The core material has managed to escape the asteroid, probably in some gigantic collision. Other M-types, though, may be different compositions altogether, and there's still a great uncertainty about exactly what all of the M-type asteroids are.
If we want to study the composition of an asteroid, one of the best ways to do so is to analyze meteorites at an automated mineralogy lab, since many of them come from asteroids. The team at the Mineralogy Lab of the Geology and Geological Engineering Department at the Colorado School of Mines can examine the compounds of any meteorite sample with extreme precision.
All meteorites are fragments of rocky or metallic matter that's been transported from objects out in the solar system, and they've landed on the Earth's surface. And we can collect them and study them in the laboratory and work out their chemical composition, which minerals they contain, and therefore we can extrapolate the resource potential of particular bodies that exist elsewhere in the solar system.
Our automated mineralogy system is SEM-based, so we're using a scanning electron microscope to basically scan our sample. We have to prepare the sample. It is really important that our samples have a perfectly flat surface. So we have to polish our samples down to 1 micron. So the surface is perfectly even, so when we have the beam interact with the sample, we don't have other interaction features that will change the result of our interaction. We have our electron beam interact with the sample, and then we investigate basically the interaction product we get from the beam interacting with the sample. The result from this interaction we compare with the lookup table, where we have definitions for all minerals and phases that are of interest to us. And then our software program, the automated mineralogy software, will produce a false color map based on the definitions written and based on how it compares the analytical data with our lookup table.
Therefore, we can determine if the sample has more or less iron, nickel, platinum, or more or less of any other mineral. All asteroids, no matter their composition, are rocky remnants left over from the early formation of our solar system about 4.6 billion years ago. So they offer us clues to unveil the most hidden secrets of our most remote past. We've been exploring and studying asteroids for decades to understand what happened before us, before life on Earth, and even before Earth itself. Asteroids, considered floating fossils, can help us trace the solar system's evolution from a primordial disk of dust and grains. Asteroids can help us understand how the planets were formed and the origin of life on Earth, since there are theories that claim that the massive impact of asteroids was mainly responsible for delivering elements of life to primitive Earth. Asteroids are not just remnants of the remote past. They are also real hazards to Earth. Some pass close by Earth and could hit our planet one day, as occurred in the past when one ended the reign of the dinosaurs.
There was a 10-kilometer asteroid 60 million years ago that hit Earth. That's one of the current stories about the dinosaur ending event. Presumably we could have another asteroid impact like that at some point in time in the future, although right now it's not showing up as likely. We haven't found it yet.
A few years ago we saw an object the size of a large office building impact over Chelyabinsk, Russia. Very much smaller scale event, but still, in some ways, devastating for that particular city.
Scientists continuously monitor Earth-crossing asteroids whose paths intersect Earth's orbit, and near-Earth asteroids that approach Earth's orbital distance to within about 28 million miles and may pose an impact danger.
The question is what to do about this. So right now, NASA has several ground-based surveys that use telescopes to scan the sky and look for threatening asteroids. They're trying to find all the asteroids that might present a threat to the Earth in the future. So far we've had some success with this, where we think we've found all of the 1-kilometer asteroids and larger bodies that can hit the Earth. But as we go to smaller worlds, we go to, let's say, worlds that are half a kilometer or 100 meters or so, these objects are still threatening. We're still working to find some of these bodies.
Bennu, the target of the OSIRIS-REx mission, is one of the most potentially hazardous asteroids to Earth that is currently known, even though its odds of colliding with Earth are still relatively small.
NASA hasn't been able to control or change the trajectory of any asteroids yet. We are really at the beginning of understanding the types of asteroids that could impact Earth and how we might redirect them, which is one of the goals of the OSIRIS-REx mission, is to understand how the asteroid Bennu actually orbits and what we might do in the future to redirect it.
In fact, there is a NASA mission, the DART mission, that will test a technique for defending the planet from a future hypothetical asteroid impact, the main goal of which is to attempt to change the trajectory of an asteroid. Currently, there is no coordinated international plan to act in the event a potential hazardous asteroid is detected. Nevertheless, there are several non-governmental organizations that are focused on this issue. One of the most active is the B612 Foundation, which works toward protecting the Earth from asteroid impacts and informing and forwarding worldwide decision-making on planetary defense issues.
There are a number of groups worldwide that are concerned with asteroid detection and defense. and one of them is the B612 Foundation.
The B612 Foundation works to make interpretation of asteroid data open and accessible, and serves as an informed source for an international community of policymakers and scientists who can best help to achieve these goals. We haven't had any of these extinction-level events in recent history, but there might be one in the future if we don't do something about it. Some of Earth's largest craters, which are millions of years old, are large enough to hold a big city or even a small country. One of the most stunning craters that was recently discovered was in a remote area of northwest Greenland, buried under 0.6 miles of ice. It's 1,000 feet deep and 19 miles in diameter, which is bigger than Paris. That crater formed less than 3 million years ago, when a meteorite more than half a mile wide smashed into that area. The devastation that an impact like that could cause today would be catastrophic. Over the last decade, governments have started to gain awareness of this threat and have begun to make progress on the planetary defense front. With the ground-based U.S. National Science Foundation's Large Synoptic Survey Telescope, the LSST, 5 years from entering service, and with the selection of the Space Telescope NEOCAM as a finalist in the NASA Discovery Mission Program, scientists will be able to track 90% of near-Earth asteroids larger than 460 feet in about a decade.
We have to do something, or one day we will not be around anymore to ponder the asteroid problem. The asteroid problem will have done away with us.
Asteroids are among the oldest celestial bodies in the solar system. As floating fossils that witnessed Earth's primordial stages, they convey key information about the origin of life, as they are believed to have delivered the elements of life to Earth during its early stages.
Asteroids are fascinating celestial bodies that are somehow misunderstood. The asteroids hold the answers to many of the secrets that can help us to understand our own planet.
In addition to asteroids, comets and other small bodies offer clues that can help us understand Earth. Comets are very similar to asteroids. Both are remnants of the very distant past, like flying fossils from the origin of the solar system. However, while asteroids consist of metals and rocky material, comets are made up of ice, dust, rocky materials, and organic compounds.
A comet is an object that shows activity, and asteroids generally don't, although there are rare occasions of asteroids that show activity as well. The comets typically have a very eccentric orbit. So when it comes closer to the sunlight warms the gases and ices in the comet and creates a gas and dust tail.
2 missions targeting comets have helped us to unveil some of their secrets. NASA's Deep Impact mission and ESA's Rosetta mission, one of the most important missions led by the European Space Agency. In 2005, some of our ideas about the formation of comets and their role in delivering the elements of life to Earth changed thanks to NASA's Deep Impact mission, which was a pioneer in the study of these mysterious and beautiful celestial bodies. The probe reached the comet Tempel 1 on July 3, 2005, and the following day it successfully released an impactor on the surface of the comet, which generated a brilliant flash of light, later discovered to be ice and dust debris ejecting from the fresh impact crater. The Deep Impact mission was the first attempt to peer beneath the surface of a comet. It revealed a number of new findings about comets and their composition, including evidence of water ice and organic materials.
The Deep Impact mission was a wonderful example of the kinds of technology that we want to have available to us in the future for deflecting the trajectory of a potentially hazardous object. Deep Impact was purposely targeted to impact the nucleus of Comet Tempel 1, not for the purpose of pushing it off course, but for the purpose of studying what the subsurface properties of that comet are like. The side benefit, of course, was this is the first time we'd ever done something like this, purposely targeting a spacecraft to slam into a small object in the near-Earth environment. And so it was a great accidental practice, if you will. It was an unintentional practice of the kinetic impact method of deflecting asteroids.
However, we had to wait almost a decade until the next mission to a comet to discover more about these mysterious celestial bodies. It was ESA's Rosetta mission, a spacecraft sent to the 67P Churyumov-Gerasimenko comet by the European Space Agency, that gave us new evidences about comets. On November 12, 2014, an unbelievable milestone was reached when it successfully deployed its Philae probe on the comet's surface. The first time in history that such an extraordinary feat was achieved. Rosetta gathered significant data on the comet. It revealed that it had a remarkable array of surface features and many processes which contributed to its activity, painting a complex picture of its evolution.
Coming in with the Rosetta mission, one of the strong motivation was whether or not comets played a role in delivering water to the Earth or potentially even organic compounds. I believe some of the outcomes from the Rosetta mission are now clearly showing that the comet didn't really play much of a role in delivering water to the Earth. We can look at isotopes of hydrogen, for instance, and deuterium on the comet, and they have distinct properties to what we find on water on Earth. And so there doesn't seem to be much room for delivery of water from comets. So that is an important aspect. Regarding the organic material, this is still an ongoing debate. Clearly, comets contain lots of organics, and so in principle, there is an opportunity to deliver organic material to the surface of the Earth, but it's totally unclear whether or not they actually played any significant role in the, let's say, formation of complex organics on Earth that eventually led to the formation of life.
The main shocking conclusion after all the data gathered was analyzed was that comets didn't bring water to Earth. Regarding asteroids, there are theories that suggest that they might have planted the ingredients for life on Earth. The key point would be to know how much water they have, which would be considered evidence of how they helped plant the seeds of life on Earth. There are two ongoing missions that may provide an answer to this question. The Japanese Hayabusa 2 mission to the asteroid Ryugu, and NASA's OSIRIS-REx mission to the asteroid Bennu. Both missions will collect asteroidal materials and bring them back to Earth for in-depth analysis.
The OSIRIS-REx mission to asteroid Bennu is a sample return mission to detect amino acids on an asteroid and bring back a pristine sample to Earth for study here.
We will learn a lot from comparing the two asteroids, Bennu and Ryugu, and understand the similarities and differences between their samples. The first one to be launched was JAXA's Hayabusa 2 mission, a mission of the Japanese Aerospace Exploration Agency that left Earth in December 2014.
A Hayabusa 2 mission is visiting an asteroid called Ryugu. It's about 1 kilometer across, It also seems to be a primitive carbonaceous chondrite. But the interesting question is, did it come from a different parent than, let's say, Bennu? It's possible that both of these asteroids came from very different parent bodies originally in the asteroid belt, but it's also possible they came from the same parent body. In the process, we're going to learn about the nature of very large asteroids that are primitive in the asteroid belt.
It successfully reached Rugo on June 27, 2018. It landed 3 hopping rovers on the surface of the asteroid. Some of these rovers have already sent home stunning images. However, the climax of the mission came on February 22, 2019. That day, the spacecraft was able to make the most complicated maneuver, the first touchdown. The probe was able to grab a tiny sample of dirt off the surface of the asteroid. It was the second time that humanity has ever achieved such a feat. These are the actual images of the historic moment of the first touchdown. Hayabusa 2 is hoping to bring back to Earth between 10 to 100 milligrams of material for in-depth analysis. The goal is to clarify the origin of life by analyzing samples acquired from a primordial celestial body, such as the C-type asteroid, to study organic matter and water in the solar system, and how they coexist while affecting each other. The other asteroid sampling mission that is now underway is NASA's OSIRIS-REx mission. On December 3, 2018, after a 1.2 billion-mile journey, it reached its asteroid target, Bennu, and started to orbit. It is scheduled to bring back a sample of this mysterious celestial body to Earth in a sample return capsule in 2023.
The OSIRIS-REx mission launched in September of 2016, and it's a 7-year mission to go out to the asteroid. So we're going to reach the asteroid in 2018 and perform science studies of it through 2019 and 2020. And then in 2021, we will begin our return back to Earth.
The OSIRIS-REx mission will answer some key questions about the origin of the solar system, since as an asteroid, Bennu is a flying fossil from our solar system's most remote past, and about the origin of life on Earth, since as a carbonaceous asteroid, it may contain molecular precursors to the origin of life and Earth's oceans.
One of the reasons why we want to find out whether or not there are amino acids on Bennu is because we're not exactly certain how the building blocks of life got on Earth in the first place. But one of the theories is that asteroids may have impacted Earth while it was in its early formations, and if those asteroids had amino acids on it, then it would have seeded life here on Earth.
OSIRIS-REx will determine Bennu's physical and chemical properties, which will be critical information to have in the event of an impact mitigation mission. It is scheduled to touch down on the asteroid's surface with the Touch-and-Go Sample Acquisition Mechanism, or TAGSAM, that consists of a robotic arm with an attached sampler head.
We use the TAGSAM arm, which is kind of like a really expensive vacuum cleaner, which reaches out and touches the surface of Bennu from about 6 feet away and uses nitrogen to stir up the dust and the regolith that's on the surface of the asteroid. And that gets collected inside of a round collection plate, which we then store on side of the spacecraft and bring back to Earth.
From the most distant asteroids orbiting beyond Jupiter to near-Earth objects, each space rock contains clues to trace the epic events that shaped our solar system as we know it today. By studying these small bodies, we can learn more about how they accreted to form larger planets and about the time period when they massively impacted primitive Earth's surface. Everything started with a primordial disk comprised of grains of dust, which were tiny particles of rock, metal, and ice swirling around our primitive sun. Asteroids can help us investigate how the planets were formed from the progressive accumulation of smaller objects.
Well, an asteroid is sort of a leftover piece of the original building blocks which made the planets. Okay, originally we think our solar system was mainly made up of gas and dust. And slowly the dust began to form in larger and larger objects and became objects very similar to the asteroids we have today. Continued to grow, and ultimately they became into planets, they became into large objects in general. But some of the smaller objects that didn't manage to get into the planets became sort of the leftovers, and they're what we know today as asteroids. So these bodies have changed very little since the earliest times in solar system history, about 4.5 billion years ago.
Asteroids can help us investigate how the planets were formed from the progressive accumulation of smaller objects. Two of the most peculiar celestial bodies that may help us understand how the planets were formed are Vesta and Sirius. They are the largest bodies in the main asteroid belt, two protoplanets that never grew enough to become planets. NASA's Dawn spacecraft, which recently ended its mission, orbited both and definitely demonstrated that they are quite different from regular asteroids.
The Dawn mission is a NASA mission that was taught to investigate with great details the main objects in the asteroid belt. The targets were the asteroid Vesta and the dwarf planet Sirius, which are the most massive object in the asteroid belt in between the orbit of Jupiter and Mars. The name of the mission tells already what the mission is about. Dawn means, really try to understand the origin of the solar system, how the solar system was formed. And these objects, the targets of the missions, were considered and are still considered to be objects that formed very early on in the solar system.
We almost call these dwarf planets. One is called Ceres, which is over 900 kilometers across. The second one is called Vesta, which is over 500 kilometers across. These two asteroids have very different compositions and a very different nature.
On November 1st, 2018, Dawn ended its mission. Currently, it's in orbit around Sirius, where it will remain for decades. Dawn found that while many asteroids are loose collections of rubble, the interiors of Vesta and Sirius are layered with the densest materials at their cores.
The asteroid Vesta seems to almost be like a little version of a planet that formed in the inner solar system. We believe it got so hot that it melted at one point, forming a core. It actually has material on the surface that makes it look like it's actually gone through volcanism, where basaltic material has come out and flowed across the surface of the rest. We actually believe we have some kinds of meteorites that actually came from this asteroid Vesta. And so we've been investigating that world to try to see the differences between what we could see from a spacecraft mission and what we can see from the samples that arrived on the Earth.
It's fascinating to think that we have a chance to directly study a piece of Vesta here on Earth. Thanks to some meteorite samples, the team of the Mineralogy Lab of the Geology and Geological Engineering Department at the Colorado School of Mines can investigate the main compounds of the surface of the protoplanet.
This one is a howardite, so it's an impact progression. And these are little bits of rock on the surface of Vesta that were smashed up during other asteroid impacts. And these bits of rocks were thrown about the surface, accreted together. They were fused together by the regolith, and then a later meteorite impact has thrown this piece off Vesta's surface and it's impacted the Earth. This sample here is a diagenite. So this is like a gabbro that we would find on Earth, and this forms at some level within the crust, and it's an igneous rock. So it crystallized from a magma at some point in time. And if we can study the chemical compositions and the proportions of the minerals that exist in,
the results from the analysis of these samples will give us their precise composition.
In the samples we have for this meteorite, you can find pyroxene, anorthite. You can find some apatite, some spinel, some quartz, of course, and those types of minerals. So the brighter the spot, the more iron content there is. So you see these gray areas have some iron content, but the most iron content is in these white spots, pixels here. So there's a good majority of this meteorite that actually has iron. There's more concentrated spots throughout it.
The Dawn mission also studied Sirius, the biggest object in the main asteroid belt, revealing that it was an icy ocean world where water and ammonia reacted with silicate rocks.
Sirius, instead, is an entirely different object. It's a much higher content of volatiles, potentially also including some water. On Sirius, we find, for instance, minerals that are the results of what we call aqueous alteration. That simply means when you have rock interacting with water, you can form deposits, for instance, like carbonates. These are common things that we find on Earth. Sirius and Vesta are considered remnants from the early solar system. By studying these objects, we can really try to understand the details of the early formation of the solar system. This object, along with many other asteroids that are found between Mars and Jupiter, didn't have an opportunity to grow to larger sizes, like a full-blown planet like Mars or the Earth. And there are several reasons why this happened. We think that the main reason is because Jupiter, which was a massive planet, is not far from this region of the solar system. Jupiter has enough perturbation to those little planetesimal, small planets that were trying to accrete in order to form a much larger object.
Thanks to several pioneering missions to certain asteroids, we have been able to learn more about the origin of our solar system, about the role asteroids played as the building blocks of planets and in delivering the elements of life. Nonetheless, some unsolved mysteries remain. One of these mysteries is what is at the core of large planets. Although we can indirectly study the deep interiors of planets for clues about their origins, it's impossible to drill down into the core of any sizable object in space, including Earth. Nevertheless, a rare object called Psyche may offer the opportunity to explore a planet-like body's core without any digging. The asteroid Psyche appears to be the exposed iron-nickel core of a protoplanet, a small world that formed early in our solar system's history but never reached planetary size. Like Vesta and Sirius, Psyche's path to planethood was disrupted. There's an upcoming mission to this unique and strange asteroid that will help tell the story of planet formation by conducting an in-depth study of this metal object. NASA's Psyche mission. The mission is scheduled to launch in 2022 and will reach its target after a 3.5-year journey in 2026. It will help us to understand a previously unexplored building block of planet formation, iron cores.
We've never actually had a chance to visit a world that's made out of iron, which may be a metal world. We think the way you would get metal worlds is possibly they are the cores that have been extracted from a larger, probably asteroid, or maybe even a small mini planet that was blown apart by some gigantic collision very long ago. So this is our opportunity to see what cores of worlds may be like. But there's also this interesting question about what should geology be like on an iron world.
The history of the solar system is written in cataclysmic events that began in the early stages of the primordial nebula that became the primordial disk of grains of dust. Giant collisions between bodies were central to its evolution. The position of the planets has shifted due to huge gravitational interactions, and these planet migrations are thought to have played a key role in the solar system's early evolution. The Trojans, as ancient remnants of that remote past that are trapped in the orbit of some planets, could help us understand what happened. In fact, Jupiter's Trojans could give us clues about what happened the last time Jupiter moved and about what role it played in the organization of the planets of the solar system.
Lucy is going to visit 6 what we call Trojan asteroids, which are these asteroids that lead or follow Jupiter in its orbit. One of the surprising things about the Trojan asteroids is that although they occupy a very small region of space, just this little region near Jupiter's orbit, they're physically very different from one another. Is that they formed at very different locations in the disk, and the gravitational evolution of the planets led to a large number of objects from that outer region being trapped in this little region.
NASA's upcoming Lucy mission, scheduled to launch in October 2021, will explore Trojans for the first time ever.
We're going to be visiting objects in both swarms. The whole idea of this is to understand the diversity of these Trojan asteroids, what makes them different, because that's going to be a key to understanding how our solar system formed. This is named after the discovery of the Lucy fossil. The Lucy mission is named after the hominid fossil, the Australopithecus fossil, Lucy, that was discovered in the 1970s. Just like the Lucy fossil revolutionized our understanding of hominid development, the Lucy mission will revolutionize our understanding of solar system formation and evolution.
Lucy's discoveries will give us new insights into the origins of our Earth and ourselves. Asteroids don't just make it possible for us to learn about the evolution of the solar system or the formation of the planets. They also offer us almost unlimited resources. They contain natural resources such as water, organics, and precious metals. In the near future, these asteroids may fuel the exploration of the solar system by robotic and manned spacecraft. They could become useful pit stops or stepping stones en route to more distant destinations like Mars or beyond. There are no gas stations in space yet, but scientists and engineers are already starting to think about how asteroids could one day serve as refueling stations for spacecraft on the way to faraway space destinations. These small worlds might also help astronauts restock their supplies of water or other materials. Asteroids are not just small celestial objects, but extremely small worlds that can help us understand our own world, Earth, as well as the solar system. They can offer us clues about its origin, its evolution, the formation of the planets, and even about the origin of life. Current technology allows us to dream of a not-so-distant future where asteroids will be pit stops for deep space exploration, as well as sources for mining metals, minerals, and propellant to be used in space and maybe on Earth. This is only the beginning of the adventure. The exploration of asteroids has just begun.